Most of what we know about the universe comes from catching light. Starlight, radio waves, and infrared are the data points astronomers use to map the cosmos. This creates a problem when studying an object so compact that its gravity prevents any photons from escaping. Einstein's theory of general relativity predicts that a sufficiently dense mass will curve spacetime. This distortion creates a boundary known as the event horizon, a perimeter where the required escape velocity exceeds the speed of light. Once light crosses this threshold, it plunges toward a singularity. To an outside observer, it simply vanishes. If black holes emit no light and trap all incoming signals, verifying their existence is a unique challenge. In theory, you would have to wait an infinite amount of time at an infinite distance to confirm that nothing ever escaped. Rather than looking for the objects themselves, researchers have spent decades searching for the violent gravitational footprints left on the stars and gas around them. The most common targets are stellar black holes. These are the remnants of massive stars that collapsed at the end of their life cycles, packing between 2 and 150 times the mass of our Sun into a microscopic point of infinite density. Many of these dark remnants exist in binary systems with ordinary stars. Because of the black hole's intense proximity and gravity, it actively strips plasma from the outer layers of its companion. This gas forms an accretion disk. As material spirals closer to the event horizon, orbital velocity increases, generating intense friction and heating the inner disk to millions of degrees. Just before crossing the horizon, this thermal friction forces the gas to release detectable X-rays. We identify these stellar black holes not by imaging the dark void, but by measuring the radiation emitted during the violent consumption of their stellar neighbors. Finding a black hole is significantly harder if it isn't actively feeding. Intermediate mass black holes, ranging from 100 to 10,000 solar masses, often drift alone through space, without a companion star to provide an accretion disk. To find these solitary objects, astronomers use gravitational microlensing. Instead of looking for light emitted by the object, they watch for light that is bent by it. In this process, the gravity of the invisible foreground mass acts as a lens. When the black hole passes between Earth and a distant star, it curves the light rays from that background source, temporarily magnifying and brightening its image. By matching these light curves to mathematical models, scientists can confirm the presence of a dark, massive object. It is proof that gravity can warp space enough to act as a cosmic magnifying glass. The largest class of these objects are supermassive black holes. Containing millions or billions of solar masses, they sit at the centers of nearly every large galaxy, dictating the motion of the stars around them. To find the one at the center of the Milky Way, astronomers targeted a compact, invisible radio source known as Sagittarius A star. Over a period of 20 years, researchers tracked the proper motions of over 100 stars as they whipped around a completely empty-looking patch of space. This plot traces the elliptical orbit of the star S2. By measuring its acceleration around the blank focal point, scientists calculated the invisible object's mass. The data revealed 4.3 million solar masses, crammed into a volume smaller than our solar system. Because there are no other plausible models for packing that much mass into such a small space, the star's motion provided the evidence needed to confirm a supermassive black hole at the center of our galaxy. The event horizon effectively hides what happens inside a black hole, but the universe cannot conceal the gravity it exerts on its environment. By cataloging X-ray flares, bent starlight, and the orbits of stars like S2, researchers moved black holes from a mathematical prediction to an observed reality. In 2019, humanity reached a new threshold in observation. By linking radio telescopes across the globe to create an effective aperture the size of the Earth, the Event Horizon Telescope team attempted to see the horizon directly. This is the resulting image of the black hole at the center of galaxy Messier 87. It shows a dark central void, the shadow of the black hole, surrounded by the glowing asymmetric ring of its accretion disk. We have reached a point where we can outline the exact boundaries of the unseeable, proving that even the darkest voids in the universe leave a trace.